Okay, let's get started. Thank you for coming to today's HAO colloquium. Our today's speaker is Dr. Rachel Osten. And Rachel is not a total stranger here. She got her PhD degree in astrophysics from CU. And actually, her research in stellar star physics started before that when she was a Harvard undergraduate student. And after that, the PhD, she worked at the National Radio Astronomy Observatory as a Jansky postdoc fellow, and then a Hubble fellow at the University of Maryland and NASA Goddard. And since 2008, she has been an astronomer at the Space Telescope Science Institute at Baltimore. And her research focuses on stellar phenomena using multi-wavelength approach. And also on the service side, she's currently the deputy project scientist for the James Webb Space Telescope. And today she's going to discuss stellar flares and space weather on other worlds.
Okay, thanks very much. Is the sound good? All right, great. So thank you very much for the invitation to come and talk to you today. This is going to be a little bit of a different flavor of talk for you, I'm guessing. Since you're used to hearing about the sun, and then I'm going to tell you the cosmic perspective of the sun, stellar flares, and I'm going to have a sort of theme of using detailed observations of stellar flares to understand not just the plasma physics on other stars, but what we can use about those studies of stellar flares to inform us about space weather of other worlds. A hot topic in astronomy these days. So let me start out with giving some motivation why you should care. This is a nice movie from the Solar Dynamics Observatory showing the very interesting plasma dynamics that goes on in the outer atmosphere of the sun. We've known now for several decades that nearly all cool main sequence stars display coronae that we think are like this. And by studying these detailed time variations in those other stars, we can get a better handle on the processes that are occurring to turn this magnetic energy into radiated energy, particle acceleration, plasma motions, and shocks, and get a better understanding of the solar-stellar connection. That's one reason why you might care about stellar flares. There's another reason, and that is that we now know that nearly every star that you can see in the sky has a planet around it. And we know that our sun influences us in this topic called space weather. And we know that other stars are going to influence their planets. In astronomy these days, the push is on to find what we call Earth 2.0, the next Earth analog, version 2. New and improved. And for technical reasons, it's easier to find these small planets around small stars. This graph shows the habitable zone, the region away from a star where you need to be located to have liquid water. You'll notice that for small stars, the habitable zone is significantly closer to the star than we are to our star. That means that anything the star can do is going to have a much more magnified effect for Earth 2.0 around a tiny little M dwarf compared to our Earth. So understanding these stellar flares will enable us to determine which of these Earth 2.0 or 3.0 or 4.0 are the potentially habitable planets that we want to spend our time and our precious astronomical resources focusing in on. And finally, those two topics might not be of interest to you at all, but it turns out that many characteristics of stellar flares share similarities with other, maybe more interesting astronomical processes. So up here, I'm showing a graphic from the SWIFT satellite, and I'll actually talk about some interesting observations that SWIFT has made of nearby stellar flares. But SWIFT was designed to study gamma ray bursts. These were, at one time, very enigmatic explosions that didn't have any explanation. Based on the similarity of these events with hard X-ray flares, there were several people who suggested that maybe some of these gamma ray bursts were actually coming from nearby stars. We now know that most of these gamma ray bursts are actually coming from the deaths of massive stars. They can be seen at cosmological distances, and they're interesting in and of their own right. And similarly, there's another hot topic in astronomy these days. There's another type of explosion, probably, something called a fast radio burst. These have not been identified so far. Based on some of the characteristics of these fast radio bursts, there have been speculations that they might actually be coming from active stars. And so in order to pin down exactly what these are, you need to have an understanding of what nearby stars can do so that you can either rule in or rule out that class of objects as an explanation. So one of the themes that's underrunning my slides today is that new facilities enable new science. This is an image of the ALMA millimeter array in the background, a newly completed millimeter observatory for astrophysics and solar physics. The LOFAR array, a low-frequency array in the Netherlands, has been completed, and I'll describe a project that I'm undertaking with the LOFAR telescope, as well as the Very Large Array, which has been around for a few decades, but it got a major upgrade recently. It's now called the Jansky Very Large Array. Same dishes, but completely new guts. So it's pretty much a new telescope. The SWIFT mission, which has been around for 10 years, has a very unique niche in observing stars and stellar flares. And the Kepler mission, which I've sort of cheekily crossed out this search for habitable planets and replaced it with a search for stellar flares. And I'll describe some of those results later on. So I'm gonna talk about flaring as one aspect of magnetic activity. This talk is going to be a little bit different from the talks that I normally give in that I don't have to explain the sun to you. I'm sure there are people in the audience who can explain the sun to me in far more detail than I can. On the flip side, though, I have to explain all of stars to you. And there's a bit of a numbers disadvantage there. There's one sun, and there's billions of stars. So I'm going to do my best to kind of provide the stellar perspective. I want to focus on using extreme events to learn about stellar flares and CMEs, and I want to highlight what we know as well as what we don't know, since that turns out to be where there's room for significant progress. And then I'll talk about habitability concerns and space weather and how these extreme events can inform those studies. So in solar-like stars, we see evidence for magnetic activity. It has many different forms, comes from different parts of the atmosphere, from the photosphere all the way up to the corona. And we know now that this activity correlates with some basic stellar parameters, convection and mass. So any star on the main sequence that has an outer convection zone, no matter how thin, is able to generate magnetic fields and produce these signatures of magnetic activity. This ranges from stars that are only slightly more massive than the sun to things that are not even real stars, substellar objects. Activity correlates with convection and rotation. This is a graph here showing X-ray emission as a function of something called the Rossby number, which attempts to use the star's rotation period corrected by the fact that stars of different masses have different convection zone depths. And there's a very nice power law relationship here between these two numbers. And finally, age and rotation. So Andy Skumanich here at HAO is one of the first people to show us that stars spin down with age. Very young stars are going to be very magnetically active based on the fact that they're rotating very rapidly. And we can see that here in this graph of X-ray luminosity as a function of stellar age. And you can see that there's a plateau at very young ages and then a decline as you go towards stars that are of solar age. However, in astronomy, we have a little bit of a twist. in that stars like to be formed, like to come together in pairs. And so when you think about the difference between a single star and a star that's in a binary, the dance of these two stars, when they're tidally locked, can maintain fast rotation even at very old ages, so even into the gigayear range. And we see evidence for enhanced magnetic activity in these, what I call active binary systems, into gigayears, even at 10 gigayear age range. So that defies a little bit the expectation for single stars that you would only see activity at very young ages. So when we do detailed observations of stellar flares, there's 3 classes of objects that I like to think of as the usual suspects. Because when you're writing a proposal and you say that you want to study the flare process in stars other than the sun, you have to convince your TAC that you're going to observe something. Otherwise, they're not going to give you time to study something you're not going to observe. So that leads to a bias to stars that have enhanced flaring rates. And based on what I told you so far, you should be able to pick these out, some of them anyway. Very young stars are rotating rapidly. They have a complication in that some of these young stars still retain the disks out of which they formed and which are still forming planets. We've got active binaries where the dance of these two stars can produce frequent and extreme magnetic activity. It was actually the topic of my PhD dissertation here at Colorado. And the third suspect are fully convective objects, these dim red dwarfs, which I also mentioned in the beginning are where we're currently looking for the next Earth-like planets. These are also capable of producing frequent and extreme flares. So this is Boulder. I can use a holistic approach here. That's what Boulder's all about. So if I do that and I look at solar flares and I look at stellar flares, I actually find fairly good agreement in several of the manifestations that we see in solar flares on the stellar side. And there's a caveat here that the stellar side is sort of across many different kinds of stars because we don't observe stars in the same way that we observe the sun. I'll note that under the first one of these items, the non-thermal hard X-ray emission, I put a check mark and a question mark. We only have one stellar flare where we've seen spectroscopic evidence for non-thermal hard X-ray emission, and I'll describe that a little bit later. But for the most part, all of these other radiative signatures of accelerated particles, different processes occurring in the photosphere, the chromosphere, transition region, and the corona that we can study in incredible detail on the sun, we also see on stars. And the exception here, which I'm going to come back to, are things like coronal mass ejections that are part of an eruptive event on the sun. When you see a large solar flare, it's nearly always accompanied by an ejection of mass, and energetic particles. We don't have constraints on those in stars, and I'll describe what kinds of observations we can make and what kinds of observations we're trying to make to solve those questions. So when we do detailed studies of stellar flares, we see evidence for the same types of processes going on in the stellar flares as we do in solar flares. And these two slides, these two plots, are examples of something called the Newport effect, seen on a flare on an M dwarf and a flare on an active binary system, wherein the temporal signature of the particle acceleration, here it's the radio signature, comes first and precedes the observational evidence for plasma heating in a way that's linked using a differential or integral form. So this confirms to us that we're seeing similar physical processes on these stellar flares compared to the sun, even though by virtue of the fact that we're seeing these flares on stars at all, they have to be scaled up by orders of magnitude compared to the largest solar flares. And again, if we look at another scaling between flare parameters, if you look at the flare peak temperature versus flare peak emission measure. This is a plot that has both solar flares and stellar flares on it. And you can see that stellar flares tend to be much hotter than solar flares, but in the range where they overlap, there is an offset, which is explainable by a geometric effect that you've got much larger fraction of the surface of the star that's involved in the flare compared with the solar flare case. When we look at energy partition fractions in solar and stellar flares, we also see similarities. It tells us that we're looking at the same process. This slide over here is a plot from the first solar flare to be observed like a stellar flare in white light. And this is a measure of total solar irradiance, which I'm sure people in the audience are familiar with. And even though the magnitude of the increase in the total solar irradiance was puny, 260 parts per million, compared with a factor of almost 600 increase in the X-ray, the white light dominates the energy budget for the radiated energy. We also see evidence that solar flares display a hot black body component in the blue optical, which is very similar to what is now seen routinely in M-dwarf stellar flares. And when you examine the energy partition in solar and stellar flares, you see good agreement between the amount of energy that goes into the corona compared with the amount of energy that shows up in this hot black body continuum. So it's easy to observe flares. It's one theme that you should remember at the end of this talk. But one question that we have is whether stars produce these eruptive events. That is, can we observe these coronal mass ejections? This is, I don't want to use the term holy grail because that gets overused, but there have been a number of previous attempts to try to observe coronal mass ejections on stars. You can imagine that with scaling of very energetic stellar flares requires very massive coronal mass ejections. And I'll actually come to this in a little bit, what the implications are for coronal mass ejections accompanying these large stellar flares. Previous attempts to try to detect CMEs on stars have not really been very conclusive. And part of that relies on the fact that they've used unusual flares rather than having a systematic approach to try to detect CMEs. So one approach has been to search for high velocity outflows seen in emission lines. Here's an example of a 5,800 kilometer per second blue shifted outflow, which is a little bit hard to see here compared to the beginning of the flare. Sorts of observations don't happen very often, so it's not clear what the statistics are, if this is consistent with what you would expect for a very massive, fast CME. Pre-flare dips are sometimes seen in the beginning stage of a light curve. Here's a recent example of some flares seen in a young cluster with a very small 1% to 2% dip lasting for a couple of minutes in 2 of these 4 flares. Again, this is something that is sometimes seen, not often. It's not clear from the statistics if this is attributable to CMEs or if they're sort of special cases. And there's a number of other things that are seen in stellar flares which have been attributed to coronal mass ejections, things like a transient increase in the X-ray absorption during a flare, which has been interpreted as extra material along the line of sight between you and the star, which could be interpreted as an ejection of mass from the star. The effect of the CMEs on the stellar environment, I'll describe that in the next couple slides. Looking for type 2-like bursts associated with stellar flares. And the last item is utilizing an association with stellar flares. Yeah?
How is a
So it's similar to the idea of that you've got some extra material in your line of sight that's causing the intensity of the star to decrease slightly. Okay. So this explanation of CME's effect on a debris disk falls into the category of an unusual event. In this case, we don't actually even know that it was a flare. We know that there was a rather unusual event occurred on this very young star. This is the spectral energy distribution of the star. There is an excess of emission at near and mid-infrared wavelengths that was attributed to the presence of a debris disk, a warm disk located as close as 0.4 AU to the star. And over the course of a year, between the time when these observations were taken and the time when these follow-up observations were taken, the debris disk effectively disappeared. The flux dropped by about a factor of 30. And this Nature paper that presented these observations tried to come up with an explanation, a physical explanation for what could have caused this, and they couldn't come up with a plausible explanation. So my colleagues and I scratched our heads and said, well, what about using a CME to remove the grains? And this paper we wrote was very back-of-the-envelope calculation showing that, in fact, if you had a flare that could charge the dust grains in the debris disk with sufficiently small gyroradii, they'd be swept up by the magnetic plasma in a CME. And you would need a significant amount of mass in the CME, 10 to the 20 grams, so more massive than any solar coronal mass ejection, but not actually unheard of if you look at what kind of scaling you would need between a solar flare, a stellar flare, and a stellar CME. So these are the kinds of observations that are not done routinely nowadays, but with the advent of the James Webb Space Telescope, with its very sensitive near and mid-infrared telescopes, we'll be seeing more observations like this, showing perhaps not quite as dramatic changes, but changes in the characteristics of debris disks that can be investigated for the influence of coronal mass ejections. Another way that we can try to observe stellar coronal mass ejections is by looking for a signature of the CME that is specific to the CME and not to a peculiar flare, like some of those previous explanations. And this is a project that I've just received funding from the National Science Foundation to embark on. So we know that active stars produce low-frequency radio bursts. These have been observed before. We see drifting radio bursts. And if you do a simple calculation of what you expect for an emitter that's propagating through the atmosphere of a star, a shock that is converting Langmuir waves to electromagnetic radiation, the observational signature of this drifting radio burst can be interpreted in light of the speed of that exciter, along with some basic characteristics of the stellar atmosphere. And so by applying some of these numbers to coronal parameters for known active stars, we can work out that we expect to see drift rates of a few megahertz per second. And this is within the reach of some of the new low-frequency astronomical detectors that are both very sensitive and have wide bandwidth coverage, so they can see a large fraction of frequency space at one time to search for these drifting radio bursts. My graduate student and I are embarking on this project with LOFAR, with the Very Large Array. We need optical observations to confirm that a flare has occurred, and then we can measure its gross properties, such as energy, peak flux, and duration. And that's actually a key component, that we don't want to just see a drifting radio burst. We need to be able to connect it to a flare, which are easy to observe, so that we can make this connection between the stellar flare and the stellar coronal mass ejection. The last bullet on the CME slide was to try to take what we know about solar flares and solar CMEs and apply that to the stellar case. There are two authors whose plots I have up on the screen who have done that. They've established empirical relationships between solar CME mass and solar flare energies. They get very similar relationships. And then if you blindly extrapolate that by a few orders of magnitude, you can reach the stellar regime and investigate what kinds of masses you would expect for CMEs that go along with those stellar flares. Another approach that you could try is to also use some solar results, but that have a little bit more physics behind it. There's two recent papers that have showed that there's a rough equipartition between the solar flare bolometric energy, that is the radiated energy over all wavelengths from the flare, and the total energy in the coronal mass ejection. These are factors of order unity. And that is a consequence, it's a natural consequence of flows and radiation in magnetic reconnection. So if you assume that there's an equipartition between these two parameters, you can explore the consequences of transient mass loss. It's easy to observe the flares. You just need a way to convert those flare energies measured in a particular wave band to a bolometric number. But once you've done that, you can basically run through published flare frequency distributions for a number of different kinds of stars, from active M dwarfs, flares seen on G stars with Kepler. I'll talk about that in a little more detail. Very inactive M dwarfs. And you find enhanced rates of mass loss from this equipartition value. And that's sort of what you'd expect, because in some sense, these are different ways of saying that big scales with big, right? If you have frequent and extreme flares, you're going to get frequent and extreme mass loss, and the cumulative effect of that is large. So I want to talk about some specific extreme events because they're very illustrative of the diversity of different kinds of stellar flares that we observe in the nearby universe. And I'm going to talk about three specific events that were observed with the SWIFT satellite. I mentioned at the beginning of the talk that SWIFT was designed to study gamma ray bursts from the edge of the universe, and in a somewhat nice, ironic, maybe confirmation of some of those early astronomers who said, maybe some of these gamma ray bursts really are coming from stars. Some of these gamma ray bursts really are coming from stars. And they also sort of illustrate the categories of sort of usual suspects that I mentioned here. Although the way that the SWIFT mission operates is not pointed. It triggers based on an increase in hard X-ray flux. And then, true to its name, SWIFT can swiftly reorient the entire satellite within a matter of 2 minutes to be able to look at the location of that hard X-ray emission with hard X-rays, soft X-rays, and using optical wavelengths. So we have an active binary system that produced one of these triggers, a nearby young active M dwarf, and an even younger M dwarf. And each of these events shows something a little bit different from each other. So for the II-PEG event, this was our first and so far only indication of non-thermal hard X-ray emission. We see soft X-ray emission plentifully from X-ray from stars and X-ray flares, but that holistic approach of solar and stellar flares suggests that we should be seeing signatures of particle acceleration from stellar flares. And in fact, we see them at radio wavelengths, but seeing the signature at hard X-ray wavelengths, where the interpretation is a little bit easier, has been elusive. So I'll just point out that in an attempt to kind of, these are sort of press release numbers, but to impress the solar physicists as well as the public, I often refer to these numbers in solar flare equivalent units, which is a little bit cheating, but it's nice to be able to say that this is equivalent to an X 4.4 million solar flare. So I mentioned that this is the flare for which we have evidence for hard X-ray emission. I'll just show you what that looks like. So this is a spectrum of the flare over a couple of decades in energy. It's fit at the low energy end by the typical 2-temperature plasma components. But it's clear that there's some excess continuum emission above about 30 kiloelectron volts that's not fit by this model. And you can fit it by using either an even hotter component that's 300 million degrees, hotter than anything we've seen on the sun, the outer atmosphere of the sun. Or you can fit that excess continuum emission with the standard non-thermal thick target Bremsstrahlung component. And statistically, the two models are compatible with each other. You can't judge a difference based on the goodness of fit. And in our paper, we suggested that this was consistent with the non-thermal interpretation. These very high temperatures require high densities or large length scales in order to have the plasma be able to exist and not just lose all of its energy by conduction. We saw evidence for the Newport effect. We saw a rough equipartition between the non-thermal and thermal energies at a very high value. And what is most odd is that this would indicate that there was no cooling of the plasma in the flare decay, despite the fact that the lower temperature components were clearly decaying, were clearly cooling in the decay. So at present, that's the only evidence that we have for non-thermal hard X-ray emission in stellar flares. The next event was something that happened a couple of years later. This is probably the largest stellar flare that we've ever seen in terms of received flux. This is an event that was seen by 2 gamma-ray burst satellites. The Swift light curve happened to catch the flare almost at the peak, and the CONUS satellite shows us that the flare actually was extremely impulsive, rising only a few minutes beforehand. And this would be equivalent to an X36 million solar flare. So this flare had a typical evolution of flare parameters, except for the magnitude. The other thing that's fascinating about this is the peak estimated X-ray luminosity. So it exceeds the bolometric luminosity of the star. Another way of saying that is that in the span of a few minutes, the bolometric luminosity of this star increased by factors of several. That's something that you expect to change on evolutionary timescales, not on minute timescales. So this is really, really amazing thing to contemplate. This was not a hot flare, and it was not a non-thermal flare. And this plot up here just shows the temporal evolution of the flux with time, and you can see for the first few minutes that it exceeded the bolometric flux. When we do one-dimensional loop modeling of this flare, we see that it's a fairly compact event, and it's consistent with the signature that we see in the white light for what we think are the foot points of this coronal loop. Then earlier this year, there was another extreme event, and this case happens to be the hottest thermal flare that we've ever seen. So in contrast to the other 2 events that I told you about, those were on what I have been terming the usual suspects. Those stars are well known. They're very active stars. They produce frequent extreme flares that have been observed before. In this case, this pair of stars, is a relative unknown, despite being in our solar neighborhood and being an extremely young star. At 30 million years old, these M dwarfs that are a pair are still pre-main sequence stars. And yet somehow they've escaped our our study for understanding their coronal structures and their flaring variability. So SWIFT triggered on an event here 2 days before my birthday. That was a nice birthday present. The peak estimated X-ray luminosity, again, exceeds the bolometric luminosity of the star. So these are excellent test cases for how these events might affect young solar systems that are still in the act of forming. The other thing that was fascinating about this is that there was an initially very large event followed by a succession of successively smaller events for about 20 days. The three events that I'm showing you are, in some sense, not comparable because things have happened in the SWIFT mission over the course of these, between these different triggers. So when the first one of these happened, no one was interested in observing stellar flares with this mission. They wanted to get back to looking at gamma ray bursts. And in fact, the EV LAC event that I showed you had some follow-up ground observations that consisted of one exposure, and then the operators at that observatory discovered that they were looking at a stellar flare, not a gamma ray burst, and stopped observing. So in contrast, for this event, there was a significant amount of follow-up observation on the ground. One of those light curves in the previous plot was taken by some ground-based astronomers in Greece doing optical observations, and there was follow-up observations at radio wavelengths as well, which, because of the peculiarities of this event, there was a large occultation in the SWIFT mission that just couldn't observe the star for a significant period of time. And the radio observations show us that this flare was continuing on to doing its simple decay. But when we look at the spectrum at the early times in this flare decay, we see that it's completely dominated by a very high temperature plasma, 300 million degrees. This is the hottest that we've seen so far. I still don't have a good explanation of how the star can produce this level of these extreme temperatures. We see evidence for white light flaring that suggests that this is also a fairly compact event located pretty close to the surface of the star. Okay. There's another way that we can observe extreme events on stars, and that's by using a satellite that actually wasn't designed to look at stellar flares. It was designed to find transiting exoplanets, the Kepler mission. But it turns out the Kepler mission, using transits to detect planets, this is an extremely inefficient way of finding planets. I've heard people estimate that something like 99.975% of all the data that Kepler has taken is not used for the primary purpose of the mission, finding transiting exoplanets. Fortunately for us stellar astronomers, you find planets around stars. And a lot of that wasted data is actually pretty useful in getting a better understanding of the stars that may or may not be hosting planets. And so the Kepler data sets have been a gold mine in trying to understand stellar flares in the white light portion of the electromagnetic spectrum. We've seen flares on K and M dwarfs, on G dwarfs. Yeah, there's the largest solar flares. These are also extreme flares with energies up to 10 to the 36 ergs. So 10,000 times larger than the largest solar flares. For one particular object that I've been studying, we have approximately 6 months of more or less continuous observations with Kepler at 1 minute cadence, which is fantastic for looking for flares. This is a G star that you can see from this overall light curve over the course of this time shows some fantastic star spot modulation, indicating that it's a very active star. Its surface is covered with magnetic fields. It produces very frequent and very extreme flares. This is a scatter plot of the flare energy versus peak amplitude for about 2,000 of these flares. And I'll just very quickly go through some of the different morphologies that we see of these flares. When we look at the flare frequency distribution for these flares, we see that it looks like there is, in fact, a cutoff in the distribution of events. That is, the power law doesn't extend to ever more energetic flares. And that's actually understandable if you think about where the energy for these flares is coming from. It's coming from lower down in the atmosphere. Yeah?
So is that possibly an observational bias as far as these flares? Is there enough observations?
We have a long enough time span to be able to rule out. We should have seen more energetic flares than we did. And that actually has been one of the sticking points in previous studies, and an inability to find evidence for a cutoff in the upper flare energy. So this may be related to the largest spot regions that the star can produce. This is from a paper actually trying to answer the question, what is the largest solar flare that the sun can produce? But it makes sense. This is about 10 to the 36 ergs, which is about right here. And this size of spot is something that you would easily see in those light curves from the star spot modulations. So now that I've shown you extreme events, extreme flares on stars, and our attempts to try to constrain the other components of an eruptive event on stars, I want to try to bring it together and tell you about why, what we know about flares and these associated events and how they can affect habitability and potentially space weather. The crux of these investigations, which have been done to date, the results on this slide and then the results on the next slide, have been application of a specific stellar flare plus application of scalings that work on the sun, and it's a big unknown as to whether they work on other stars. As I mentioned, we don't have constraints on stellar coronal mass ejections or energetic particles, and it turns out that those are the two most important contributors to these habitability concerns or space weather. And so in the extreme, these sorts of things are habitability factors, but turned down by a couple of notches if those CMEs and those energetic proton events do not accompany the flares, then they're merely nuisance events or space weather, things that would make life more interesting for any inhabitants of these planets, but not necessarily cause mass extinction events. So in this paper, Antigona Segura modeled the effect of a large UV flare seen on an M dwarf. And she did this two ways, investigating the impact on a terrestrial planet with an Earth-like atmosphere. If you have the UV flare only, the ozone depth decreases by a small amount, a percent or so. But the atmosphere of the planet can quickly recover and no significant influence. When you apply the X-rays and the protons, you get a massive loss of the ozone layer in this Earth-like atmosphere, and it takes the planet tens of years before it can recover to the level that it was before this event happened. So this is potentially catastrophic. Similarly, these folks did a study of what you would expect from a planet around an M dwarf, where the planet has to be close enough to the star to be in the habitable zone, and yet being that close to an M dwarf with frequent and extreme flares, and by extension, frequent and extreme coronal mass ejections, would effectively mean this planet is bathed in a very intense stellar wind, a very dense stellar wind, that could compress the magnetosphere of the planet and expose the atmosphere to ionizing radiation. In the absence of these coronal mass ejections, though, the planet could be better protected from the effect of the star. And finally, this is something that not necessarily pertaining to flares by themselves, but it's a very interesting prospect to consider. That I have in the background a slide showing how we would determine that when we're looking at the atmosphere of an exoplanet, we are seeing a potentially habitable planet. There's a number of different markers that we look for: water vapor. The James Webb Space Telescope, which is going to be launched in 2018, will be able to find signatures of water vapor. Oxygen and ozone are considered to be biomarkers since they're produced by living organisms. And there's a number of other spectral signatures that you can look for to try to confirm that you're looking at a habitable planet. However, several people have noted that M-dwarf planets, planets sitting around M-dwarfs, could experience a significantly different chemistry than what we see here on the Earth. And you could actually have abiotic generation of oxygen and ozone in these planets that would indicate nothing other than you're sitting in around an M-dwarf. So that depends on the fact that these M-dwarfs have very high far ultraviolet fluxes, and the ratio of their far ultraviolet flux to near ultraviolet flux is enhanced. So that's not necessarily related to flares per se, but it's an interesting prospect that underscores the need to understand these stars better. Okay, so I'll conclude by just saying that there's fertile ground for solar and stellar flare comparisons. I've discovered over the course of my career so far that when I talk to other stellar astronomers, I found something that's somewhat unusual in that many stellar astronomers don't actually read solar physics papers. So when I'm a consummate consumer of solar physics literature, if only just to get extremely jealous of a level of detail with which you can do observations on the sun and still have many questions remain unanswered. But this is definitely one area where talking to solar physicists and space weather modelers and understanding what the constraints that we have from the one star-planet system where we do see evidence of the sun affecting us can help us then extrapolate to the universe of situations where that could or could not be the case. We have yet to find a systematic way to detect and study stellar CMEs. That was one of the take-home points that I hope you remember. I think that we have good prospects for being able to do that in the future with drifting radio bursts at radio wavelengths. This has the advantage that it's actually a null result is still a very important result. If we can rule out the solar connection for coronal mass ejections, that's actually says something very, very strong about the influence of these flares on the planets that might be around these M-dwarfs. Finally, this was something that also was underrunning many of my slides, is that if we want to understand the planets that we're now finding in droves in the universe, we need to have a better understanding of the stars around which we're finding those planets. And in particular, when you're thinking about habitability and space weather, having this solar-stellar connection is really important. So I'll stop there and take questions. Thank you for your attention.
Okay, Rachel, excellent talk. I
Thanks.
really strongly support your conclusions and the interesting results that you presented. And I basically have two comments. One is on the whole question of impact of stars, stellar radiation on the planet, the atmospheres of planets. One approach in trying to figure out what the radiative, shall we say, input to a planetary atmosphere is to extrapolate from the sun. Another way is to observe. Mm-hmm. And the observations are difficult because for the following reason, namely many reasons. One is Lyman alpha dominates the far UV, certainly does in the sun, does in stars too. But the interstellar medium absorbs most of the Lyman alpha radiation, so if you just use the observations, you come up with much less in the way of far UV influence on a stellar atmosphere. The Segura paper, I think, has that problem. There's a newer set of papers in which one, in effect, estimates what the total Lyman alpha flux is before the interstellar absorption. And there's a paper now published by Yamila Miguel and collaborators, I'm one of them, 2014, that shows that effect. So that's one thing I want to point out. The second is the whole question of extrapolating CMEs from the sun, the range of variability that we see in the sun, to stars, many, many orders of magnitude, is fraught with problems, as you well know. And when I read the Drake et al. Paper, 2013 paper, where he does that extrapolation, he comes up with enormous mass loss rates for these active M dwarfs and an energy budget that in the CMEs that exceeds the bolometric luminosity of the star. So that can't be. So I need to read your paper with Wolk, 2014 paper. Have you done things in a different way than Drake did?
So what we do,
to avoid that big problem.
So we end up getting large CME-induced mass loss rates, and it's by virtue of the fact that you're scaling with big flares. Frequent large flares imply frequent large CMEs. So this is so when I was talking about our observational attempts to directly constrain the CME rate, we can actually confirm or refute those results and say that, you know, there are several reasons to suggest that those results are astrophysically unsound, and yet if you follow the scalings, that's what the implication is. So if we don't observe any type 2-like bursts from stars, then that would suggest that perhaps these stars, because of their very strong magnetic fields, we know that these magnetically active stars have strong surface fields, that perhaps in this event, the radiation can escape, but the flares don't erupt.
So following along in that line of thought, the coronal mass ejections and something that you didn't really mention, but it's associated, not just the background stellar wind, play a very crucial role in the sort of removal of stellar atmospheres from young planets in solar systems that are forming. I'm thinking of Mars in particular. There's a whole MAVEN mission that's devoted to understanding the photoionization of molecular species in the atmosphere of that star, and then the carrying away of those ions picked up by the solar wind. So that's a very important aspect of the interaction between a star and its planets. But of course, it depends on whether the wind is more or less in the equatorial or in the sort of the ecliptic plane, or whether it might come out the poles. And particularly in these very young stars, that's certainly a possibility. Now, related to that, and I think very important to this whole discussion, is the fact that stars spin down over their lives. They lose angular momentum by a mechanism that's thought to be associated with a stellar wind, and by implication also coronal mass ejections. So if you have a very substantial mass loss in coronal mass ejections that are magnetically coupled back to the star, you would just naively expect a very fast spin down rate in the associated stars. Now we know in M dwarfs that their spin down rates are very long. I mean, the spin down timescales are very long compared to like solar type stars or K type dwarfs. Now, of course, the possibility is that the mass loss is primarily polar. So there's two different components there that you're talking about. There's mass loss and there's angular momentum loss. You can have mass loss without angular momentum loss.
Yes, going in the other direction, Terry and I heard an interesting presentation by Carl Schreiber taking the kind of data that you're showing on the upper limit of the size of spots and so forth and activity levels, energy loss from stars, and extrapolating to what that says about the probability of extreme events in our, from our sun. And do you have anything to add to that kind of study? It seems like you have a wealth of statistics.
I was a co-author on that paper, so.
Okay. Okay, so.
Yeah, so there the idea is that we can use these many observations of these active stars to try to, exactly as you said, look the other way and pose the question, what can we use? Can we use this information to constrain the largest flare that the sun could produce? And we have, it's an interesting approach that has some difficulties associated with it. And one of which is that it's not clear that these very active stars, that even if you try to scale down their flares based on their underlying X-ray luminosity, their underlying quiescent emission, you still end up with flare rates that are higher than what we see on the sun.
Just a little detail. I noticed in one of your first plots where you showed a solar flare in TSI, you had observed in all kinds of indices. And in the TSI, the signal dipped and then went up, so that it looked like it was symmetric in time, actually. Was that just a reduction of source data?
Those are details which are beyond.
Maybe we can defer to Marty.
So the magnitude of the flare is small enough that you see the other effects that you see in TSI data.
Yeah. Okay. Okay.
Good talk, Rachel.
Thanks.
Any unique way to detect these things that we call coronal dimmings that are almost unambiguously go along hand in hand with CMEs? So it's, as the mass is expelled, the corona vacates.
Yeah.
For some fairly lengthy period of time, the corona refills. So by being able to detect those, you could probably have a guesstimate of how much mass is ejected.
So I've talked about this with Hugh and Hugh Hudson, who is very interested in whether we can observe these coronal dimmings on other stars. The magnitude of the dimmings is fairly small; it's a few % at most, and the astrophysical extreme ultraviolet mission, which was a fair part of my PhD dissertation, was based on using data from that Extreme Ultraviolet Explorer. That's the applicable astrophysical mission that you would look at for an analogous signal, and it's just simply not sensitive enough to be able to see those kinds of effects.
That would be the most obvious marker.
Unambiguous marker. Yeah, so that was the point I was trying to make. We need something that's associated with the CME and not with a peculiar flare. Yeah?
You mentioned that the habitable zone of an M dwarf is quite a bit closer to the star, and sort of implied that future missions suggest that that's where we might find the next Earth analog. I wonder if you might discuss how do you assess the habitability of a planet that's inside the tidal locking radius?
Yeah, so that's a very good question. So planets that are inside the tidal locking radius are going to probably have very weak magnetospheres. That was the crux of the argument that the effect of an enhanced CME rate on these M dwarf planets. That their magnetospheres are not going to be able to protect themselves against this onslaught coronal mass ejections.
But only one side of the planet.
That's true. That's true. Yeah. So there's been a lot of modeling of what these planets might look like, and if they're tidally locked and they're always facing the same side of the planet facing their parent star, there's going to be extreme temperature differences between the day side and the night side, and it appears that you can mitigate that effect with a very efficient circulation pattern in the wind speed on the planet that can redistribute the radiated energy from the hot side to the night side and keep things still pretty toasty, I think. And those kinds of planets, you might be better served to look near the terminator, where there's more of an equilibrium between the two, between the day side and the night side.
Studied did not include sun-like stars.
Yes.
There's an obvious reason for that I'm missing. Why is that?
So remember I said they're the usual suspects, right? Young stars, active binaries, M stars. That doesn't include solar type stars, unless they're very young.
But we're interested in.
We are very interested in. So one of the slides that maybe I went through it a little too quickly. The Kepler results. So there's this graph here from Mehara. This was a Nature paper where they looked specifically at G-type stars to look at their flares with Kepler. One of the things that I didn't emphasize in the talk in particular, I talked about how there's a bias in the types of stars that we study for flares. But so it turns out that things like Swift and things like Kepler actually remove some of that bias because they're not pointing at particular stars. Kepler pointed at 125,000 stars during the main phase of its mission. And so, that actually a fairly small percentage of those stars were the fully convective objects that would dominate these kinds of flare samples.
Okay. You're the assistant project scientist on JWST, and you're very interested in active stars. So my question is, what do you think JWST will tell us about stellar activity?
Oh, let's see. So
what is the overlap?
What's the what?
What is the overlap?
What's the overlap? Well, there's the potential to see some of these very interesting debris disk events that might be related to activity. The idea of looking for temporal variations in stars in the infrared is something that's really still a new concept. It's something that only kind of got some grounding with the Spitzer mission in very young stars, finding evidence for disk variations. But it's not something that's really caught on. The traditional ways of looking at stellar flares don't include the infrared, even though for M dwarfs, that's where the peak of their spectral energy distribution is. The types of observations that you can do from the ground to study whether there is a radiative signature of flares in the infrared have actually not been very constraining. I'm aware of a paper from a few years ago by the Washington group that tried to assemble basically ground-based photometry from the U-band all the way into the infrared. But because of the nature of the infrared detectors and the fact that these stars are so bright, their effective integration in the infrared and the near infrared was a second or two over the course of in comparison with shorter wavelength observations that had cadences of several tens of seconds and could actually see the influence of the flare. So there's been some recent work in solar flares. Again, this is where reading the solar literature and finding interesting events or interesting signatures that we stellar astronomers can then try to see if there are stellar analogs of. There have been some detections of an emission line at 1.5 microns during solar flares. Tom might know something more about that. So it's in some respects with flares, it's sort of terra incognita.
You mentioned many stellar flares are much more energetic than solar flares.
Yes.
And I think I understood primarily because those stars are much hotter than the sun. On the other hand, on this slide, the G dwarf stars also produced lots of super flares, and on the other hand, we do not observe super flares generally in the sun. So what's the reason for so many super flares in the G dwarfs but not in the sun?
When I said that most of the stellar flares that you observe are much more energetic than solar flares, actually by virtue of the fact that you have a 1 over r squared distance diminution when you go from looking at a star that's at 1 astronomical unit from you to stars that are parsecs away. Just by that very nature, the types of flares that you're going to be seeing from stars are orders of magnitude more energetic than what you can see on the sun. So, and we don't have an understanding of why these G stars are producing these very energetic flares. One thing to note is that some of these G stars could in fact be binaries, and so those having a companion that's close enough to it to induce tidal locking could enforce fast rotation and enhanced magnetic activity, and those would sort of remove those sorts of objects from the things that you would consider to be truly solar analogs. But we need to follow up these solar type stars so that we have a better understanding of what they are. Tom?
One way to really kind of pump up the ergs there in a flare is to have a long duration flare instead of an impulsive event. So is there, I'm not enough familiar with this, and I should be, is there a change in the sort of the relative proportion of short duration versus long duration events as you go to more and more active objects?
You know what? That's a good question, and I don't think we have enough of a database to be able to explore that in a systematic fashion. But that's an interesting prospect. I could imagine using the Kepler database to pull out flaring stars and do look at the characteristics of the flares on stars of different spectral type, stars of different underlying magnetic activity levels, and see if there are some systematics. I mean, we've certainly seen evidence of very long duration flares that can last for days.
You have to tell a story about that. So Rachel was my student back in the day, and we were looking at I guess it was Beta Ceti with the Extreme Ultraviolet Explorer, and Rachel, we had a fortnight of observations of this particular active K giant star, and Rachel would come into my office every day and show me the plot of the previous day's observation, and it'd be a little squiggly line going in some direction, and the next day there'd be a little squiggly line going in another direction. And to me, it was all pretty boring. I mean, I didn't see that this project was really going to go anywhere. But at the end of the 14 days, Rachel came in with a different plot that put all of the days together. And then when you looked at it in a compressed time waves, there were two huge flares that just lasted for days and days. And you don't see them with a resolution of 1 day. You really have to look at a much longer baseline. And this led to studies of a number of other of these very active objects with very long duration flares. But they're giant stars.
Other questions? All right. Thank you, Rachel, again. And actually,
Thanks.
Concludes the last talk of this season. And if you had any suggestions for next season, please let me know. Thanks. The colloquium season. Thank you so much.
Good.